Let us start. We have gone through the shear stress and bending moment diagram. Then we have started what is the bending stresses involved due to the action of bending moment, which is nothing but a couple acting on a longitudinal planes on different section of the beam. Now, due to the action of this bending moment, the beam is subjected to stresses that is called bending stresses, which is supposed to be for a particular section of a beam. It is supposed to be compressive in the inner section and tensile in the outer section. And there is a particular plane over which this there is no stresses exist. That plane is defined as neutral planes. And this is the conception of neutral planes is most important for the consideration of shear stress and bending stresses, because we are thinking that we are taking into account and we have proved that the shear bending stresses in different fibers of the beam across any cross section depends on entirely on the distance from the neutral axis. It can be higher in the stresses, higher is the distance, higher in the neutral axis. Now we have done bending equation, which takes into account the relation between bending stress and bending stress and bending moment of the concerned beam member here. This is defined as the bending equation or equation for bending, or bending equation, which is giving the relation between the bending stress of the concerned fiber, and the concerned fiber is defined by the distance x from the neutral axis across any cross section, and this is the bending moment on that particular position of the beam. I is the moment of inertia of the cross section. E is the Young's modulus, and radius is the R is the radius of the curvature of the bending, which causes on this particular position of the section the action of bending moment there. Now, there is another important definition. This is defined as section modulus, where the ratio I by Y, where I is the farthest or the most distant point, of the section of the neutral axis is defined as section modulus. These analytical formulas and analytical relationships are important for finding out the bending stress concerned in different position of the across the cross section of the beam. This is denoted, section modulus is denoted by J, and it is defined as the moment of inertia about the neutral axis divided by the distance of the farthest point from the neutral axis. And over each, this formula constant bending equation reduced to M is equal to sigma divided by I divided by I, or M is equal to sigma multiplied by J. The maximum moment which also can be carried out by division section for a given value of the stress, given value of maximum value of stress is defined as the moment of resistance. So in another way, if we have the maximum value of the stress in a particular section, the bending moment created on that particular section is defined as the moment of resistance. Now, we are supposed to know, we have to know the moment of inertia as per the bending equation. We are supposed to know the moment of inertia I, which is defined as a of a momentum is defined as the summing of the products of various particles with the square of the distance from a different axis, or moment of inertia, or is equal to second moment of inertia. Inertia is defined as the area concerned and area and distance multiplied by area multiplied by just 1 second, area multiplied by the distance of the area from a particular frame of reference, from a particular reference. Now, with these conceptions, we have to know the bending moment of inertia of different types of section, which we have gone through in earlier classes. And now we are supposed to apply this conception in the analytical problems. Say the problem number 5.5. What we have here, a 200 by 200 millimeter by 800 millimeter I-beam is used as a simply supported beam of 6.5 millimeters span. Now, the wave thickness is 8 millimeter and the flanges are of thick 50 flanges are 10 millimeter thickness. Determine what is the concentrated load that can be carried out at a distance of 2.5 millimeter from one support if the maximum permissible stress is 80 MPa. So what is given? It is an I-beam. I-beam, it looks like this. It will be given up in the problem here, and is a size is 200 by 800 millimeter I-beam. 200 is the height here, 200, and 8 millimeter is the width here, 8 millimeter. It has flanges, means this flanges, this is the flanges, their thickness is and 10 millimeters, and wave is thickness, wave is here, the thickness is 6 millimeter. So what we have to do, we have to calculate, just 1 second, let me erase because it is not necessary. So what we have to do, if we have a beam like this, which is supported at the ends, and we have to find out the maximum permissible stress, which is given as 80 MPa. The concentrated load, we have to find out the value of the concentrated load, which is carried out, say at a distance, say this is W, it is at a distance 2.5 meter from one end. And but this is the application of this, what will be the maximum load that can be applied if the maximum permissible stress across the cross section of the beam is 80 MPa. So first of all, let us go through the figure, and an I-beam is shown here. Now, the maximum load distance 2.5 per one support. So maximum support is given, maximum permissible stress is given as 8.89 MPa, and maximum point load is supposed to be placed on 2.25 meter from one end, and the I-beam cross section of the I-beam is given. So what we have to find out, the moment of inertia of the cross section, that is moment of inertia of the I-beam, which is that our cross section, which is our given cross section. So the as per from the I-beam figure, which is more clearly visible here, the depth is 200 millimeter and width is 80 millimeter. So as per our rectangular, as per our theory of the moment of inertia of the rectangular cross section, by the width multiplied by the height, 3 times the height divided by 12 is the moment of inertia of the particular section. As we know, the width is 80 millimeter, and as we know, the height is 200 millimeter, and so 80 multiplied by 200 millimeter to the power 3 divided by 12 is the I-beam of if the moment of inertia of a rectangular beam with 80 millimeter width and 200 millimeter height. But I-beam is not in the shape of an eye, not like a rectangle, so we have to omit the remaining portion of the rectangle, which is not remaining portion of the moment of inertia, the remaining portion of the rectangle, which is not the part of the I-beam. So you have to find out the area of that portion also. So we have to, how do you know? Width of that portion will be 74 multiplied by the width of the flange, which is given as 80 minus width minus the web thickness, that is 6 millimeters. So 74 millimeter multiplied by the 200 minus 10 millimeter into 10 millimeter. The two flanges are there at the two end of the I-beam. So the height will be 800 into 180 millimeter, 180 to the power cube. So we have to omit this moment of inertia from the moment of inertia of the rectangle of with size 80 into with base 80 and height 200 millimeter. So give us the moment of inertia of our concerned I-beam, which will result as a value equal to 17.37 to the power 6 millimeter to the power 4. Now, if W Kn is the concerned load, so that the reaction of the supports are W by 3 and 2 by 3. So here what we have, this is the point load at plotted W situated at this particular point here, which is away by 2.25 millimeter from the right end and away by 4.5 meter at the on the left end, where the full length of the beam is given as 6.75 meter. So the constant load IB will create reaction at the support at the left end and at the support at the right end. And as if we can take the reaction, if we can take the moment about one of the ends, say from this side, it will be reaction at A multiplied by the reaction rate A multiplied by the distance 76.75 divided by is equal to W, the point load, multiplied by this distance 2.25 load, which means this is W by the reaction at A will be W by 3. And if we calculate, omit this W by 3 from the W, as this is W is equal to W RA plus RB. So RB is equal to W minus RA, where RA is equal to W by 3. So RB will be equal to 2 into W by 3. So if we don't know that, if we know the value of W, we can calculate the value of the reaction at A as well as at B. Now, so what will be the maximum bending moment? The determination of the load, the maximum bending moment will be W by 3 multiplied by 4.5 meter. That is 1.5 W. That is 15 kilonewton. So how it is possible? So if you take a section and take a section here at a distance x and find out the bending moment across all this section, you'll find that the bending moment will be maximum at 4.5 meter length from the left side, which we have gone through this process of calculating a number of times. So this is easily available. So W by 3 multiplied by 4.5 is equal to 1.5 W kilonewton per meter, or 1.5 to W 10 to the power 6 Newton per millimeter. So if you put this value of M here and I here, where sigma is equal to sigma divided by M divided by I, or sigma is the maximum permissible stress, that is 80 MPa, divided by I is the distance of the maximum fiber, which is away from the section excess by 100 millimeter from this end. So at 100 millimeter. So 80 by 100 is equal to M, is equal to 1.5 W 10 to the power 6 Newton per meter square, divided by the I, which is already calculated 17.37 into 10 to the power 6, or W is supposed to be 9.264 kilonewton. Let us go for the next problem. (5.6). What is given here? A rectangular is supposed to cut from a cylindrical log of wood, means a round a log of wood of round cross section. So which is like a cylindrical, which is whose cross section is round, but not square or not rectangle. And we have to cut our rectangular beam from this log. After rectangular beam from this log, so that with diameter, and we have to find out the diameter d to determine the ratio of the depth to the width of the strongest beam which can be had from this log of wood. So what will be the depth? For as we have to make a one rectangular beam here, we have to find out what is the depth and what is the width and what is its ratio, which is the strongest from strong, which is the strongest which we can cut from the log of wood. Now, cylindrical log of wood means a prism of certain length, which is not our concern, but of square round cross section or like cylindrical cross section or round cross section, and of diameter is equal to d, which is supposed to be known to us. Now, let d. Now the d is the diameter of the cylindrical section of log, and b and h. B is the width and h is the height of the beam, which is supposed to be made as the strongest beam. Now, what will be a b? B is this width, so b will be 2 into d by 2 cos theta. This is the angle constant. This is the angle constant, and d, this is the radius of the log, which so this length will be equal to d multiplied by cos theta. This multiplied by d multiplied by cos theta, or actually d divided by not d but d by 2. D is the diameter of the log. So d by 2 into cos theta multiplied by twice as the width is from here this end to this end. So you have to multiply by 2. So it has become d cos theta. And h is supposed to be the same d by 2 sin theta multiplied by 2. This is the height, and this height should be made twice. So d by 2 into d by 2 sin theta, so d sin theta. So section module is supposed to be the bending moment divided by the maximum width, the bending moment divided by maximum distance. So b into that is for rectangular section, we have already find out. It is b into h squared divided by 6. So d multiplied, put the value of b here, d multiplied by cos theta, and multiplied by d sin theta whole square divided by 6. So d cube into cos theta into sin cos theta sin cos square d, that is become d cube. P into d square, d cube cos theta into sin square theta divided by 6. So what will be this is the section modulus. So what will be the strongest section? For the beam to be the strongest, section modulus must be maximum. So d divided by d into z divided by d theta is equal to 0, or d divided by 6. So you have to find out what is the maximum section modulus in order to make the maximum strength maximum in the for case of beam. So d divided by d theta, we have to find out what will be the maximum angle which can be subtended here, which will give us the maximum value of d and h. So then d theta by dh is equal to 0. So d to the power dx by 6 minus sin square theta. With cos theta, if we make that derivation, it will be minus sin theta. So it will be minus sin theta into sin square theta. So minus sin cube theta plus cos theta will be equal to 2 into sin theta multiplied by cos theta. Thus, this becomes sin square theta. This is equal to sin square theta 2 cos theta, or tan sin square theta by 2 cos square theta, or tan square theta is equal to 2, or tan theta is equal to square root by 2. Which gives sin theta is equal to square root of 2 by 3, cos theta is equal to 1 by square root of 3. Next, b is equal to, thus sin theta cos theta is like this. So we can put b is equal to, where b is equal to d cos theta. So you put the value of cos theta, t by square root of t divided by square root of 3 is equal to 0.577 to t, and h is equal to 2 divided by 3 by 2t. 2 divided by 3 to the power square root multiplied by t is equal to 0.817 t. Let's go to the next problem. That is 5.7. Just 1 second, please. Now, let us go through a hollow circular bar used as a hollow circular bar used as a beam has its outside diameter thrice the inside diameter. So the bar concerned here is hollow. So it has outside diameter 3 times the inside diameter. It is subject to the maximum bending moment is equal to 60 kilonewton. So determine the inner diameter of the part if permissible bending stress is limited to 120 MPa. What is given? The diameter, the relation between the outside diameter and inside diameter is given. Capital D is equal to 3 into D, and bending moment maximum constant will be 60 kilonewton per meter, and sigma is equal to 120 MPa. And sigma maximum permissible bending stress sigma is given to 120 MPa. So section modulus, we know the moment of inertia divided by the distance of the maximum fiber. Here the distance of the maximum fiber is the maximum outer radius, that is d by 2, and the moment of inertia of the circular hollow section is pi by 64 d to the power 4 minus d square. So section modulus will be I divided by y. So pi by 64 d to the power 4 minus d to the power 4 divided by t by 2. So this becomes pi by 32, and as we know that the outer diameter is 3 times the inside diameter, it will be 3 to the power 4 minus this to the power 4 by 3d, or 3 pi or 5 pi. That is as if this will becomes 9, 27, 27, 81. 81 d to the power 4 minus d to the power 4. That is equal to this into multiplied by pi by 32 divided by 3 into d. So this will become 80 d to the power 4 divided by 3 into d into multiplied by pi by 32. So this becomes 2 into 3, 2 into 16, and this 16 will cancel it as 5 to the power 4. So pi to the power 4 divided by 3 into 2, that is 6. That is the sectional modulus of this type of circular, hollow circular beam. So applying the bending moment, Zx is known, bending moment divided by sigma. So pi by 60, the bending moment given, multiplied by 6 to make it millimeter, and in Newton, make it Newton millimeter, 16 to the power 6 divided by sigma is given as 120 MPa. So Zx becomes 500 square into the power 3 meter cube. So Zx is, we know, we have just calculated 5 pi to the power 4 divided by 6 is equal to 500 to the power 3, or d cube, d is equal to 57.6 millimeter. Let us go for the next problem. A 200 into 120 millimeter I beam. A 200 into 120 millimeter I beam. It is given that the width is the B, the width, and this is the H. This is given here, and not the wave as well as flange. This is flange and this is wave. This is wave. This is flange. Now, it says to be used as a cantilever 3.6 meter length, cantilever means it's a bar will be constant like this, as is shown in the underway. This is a bar here. It is free at one end here in this type of problem and embedded here, and it is uniformly distributed load which can be carried out by the beam if the permissible stress. So you have to find out the maximum uniformly distributed load which can be carried out by the beam. The permissible stress is 125 meter per MPa and I is given as 75 into the power 6. Next, if the cantilever is strengthened by 10 millimeter thick steel plates welded at the top and bottom flanges to withstand 40% increased load, find the width of the plate and length over which the plate should extend, the maximum stress being the same. So here first we have to know, here 120 is given, 120 is the actually what is given shown in the problem. 120 is not the height, but 120 is the width. Just opposite, just I have told you in this moment. This 120 is the width here. That is the width or B breadth, and 220 is the height here. Actually, if it is given in opposite side, we have to understand because the height must be more than the width. So this is the, if it's only this is given the 20 by 120 millimeter I-beam section, we have to assume that the smaller the dimension is the width and higher the dimension which is given is equal to height. So here, based on this assumption, we got 280 from distance from this end to this end is given as 280 millimeter, the equal to height, and distance from this end to this end is given as 120 millimeter, that is equal to breadth. So first we have to find out what is the maximum value of the distributed stress which is which this beam can carry out by the max, if the maximum permitted stress is 125 millimeter and I is also given as 75 into 10 to the power 6. So for this thing, I is already given 75 into 10 to the power 6, so we don't have to call 70. And maximum value of the permitted stress is given as 125 millimeter MPa. So uniformly distributed load for the simple beam, we have to find out the uniformly distributed load of the simple beam, and again width and length of 10 millimeter thick plates at top and bottom flanges for 10%, 40% increased load. Now, so let us assume that W is the uniformly distributed load in per meter length, load in Newton per meter length. The moment of the section, moment of resistance of the I section, or moment of the resistance, we know that is W L square by 2. What is the moment of resistance? What is moment of resistance? Is moment of inertia. Moment of inertia of resistance, just we have discussed. Moment of inertia on this section where bending stress is maximum. So moment of resistance W L square by 2 is given as so we have to find out the moment of resistance is equal to moment of inertia, that is for a distributed load or cantilever beam, is equal to W L square by 8. So L is the total length of the beam, which is W into 6 multiplied to the power 2 divided by 2, 6.48 into W Newton meter, or 6.480 W Newton per meter. Now, sigma by Y, is equal to M by I. So sigma is the maximum bending stresses are 120. Y is the distance, is the end of the fiber, that is the from the section to the outside, which is given as 280 millimeter, and from here to this end is given as 120 millimeter, 140 millimeter. So that is the maximum distance y. Or so in order to get the maximum bending stress, sigma by y, M by I, where sigma is given 125, y is given as 140, and M is given by 6480 W, and I is given as 75 to the power 6, or W is equal to 10 into 334 Newton per meter, or MR is equal to 6.48 into 10 into 334 is equal to 6.964 Newton meter. So we have got the value of Y, then we have got the value of the moment of resistance as 6.8 into 10 into 10 into 10,103,334 is 66,964 Newton per meter. Next, we have to consider about that. We have to take into account the moment of resistance of the straight section. When load increased by 40%, when the load is increased by 40%, that is W. So W will be 10 into 10,10334 10 to the power into 1.4. That is 14468 Newton per meter. So Y max will be increased because the thickness of this beam will be 10 millimeter, is given as 10 millimeter. So Y max will be 140 plus 10 into 150. So MR here concern will be with this increased load and increased value of the Y max will be defined as MR W 14648 into 3 into 6, that is the length remains unchanged, divided by 2, or is equal to 93.75 to the power 6 Newton per millimeter square. Now, sigma by Y is equal to MYY. The sigma is given as 125, which is not changing at all, and Y is increased to 150, and I is given here, and M we have calculated that 93.75 to the power 6, and IL is given as is supposed to be calculated here, because L is not given as we don't know that all the dimensions of the additional plate. So I is equal to will become 112.5 to the power 6 millimeter square. The required increase in moment of inertia is 112.5 into the power 6 minus 75 into the power 6, that is 37.5 to the power 6 millimeter to the power 4. Now we have to calculate the width and length of the plate. Let B is the width of the steel plates. In both the plates was the same, but unknown. So width of the plate will be B, the width multiplied by this thickness is given as 10 to the power 3 divided by 12. As it is in both sides of the beam, it is multiplied by 2, plus the constant beam member, area of this member is B into 10. B is the width multiplied by 10, and its distance of this main point is equal to 145 into 10, 145 to the power square. It is the bending moment, moment of inertia of the concerned plate. Into those are multiplied by 2, which is given like this, which can be explained like this. First of all, you are calculating this moment of inertia of this side, B into 10 to the power 3 divided by 12. But both there are two in point, one is here, another here. And then if we consider the full section of the beam, you have to consider the bending moment of the remaining portion of the beam also. So we have to calculate the area multiplied by the remaining portion. Area is here, B into 10, that is the area, and this distance is 145. The moment of inertia from this section is from here to here is given as 145.2, because we know that we are taking the square moment of inertia, the second moment of inertia. So here After calculating, this is equal to the increase in bending moment, which is given as 37.5 into 10 to the power 6, or B is equal to 89.1 millimeter. So we have calculated the B, and with increased load but without cover plates, let the value of the bending moment, the maximum permissible value of 66967 bending moment at section X from left hand. So Wx square by 2, the bending moment, 14468 by x into x square by 2 is equal to 66964, or x is equal to 964. That is the increase in the bending moment. Maximum permissible value is x. So what we have find here is the maximum permissible value of the bending moment, which is 66964, 66964 Newton per meter. The maximum value of the bending moment is at the fixed end, and thus the plates are to be fixed. So x is equal to 3.34. So the maximum value of the bending is at the fixed end. Thus, the plates are to be fixed at a distance 3.6 to minus 3.04, that is 0.56 from the fixed end. This is the answer. Next is another problem of same type, but the support is a bit different. A 430 into 160 millimeter I beam is to be used as a simply supported beam of span 9 millimeter. So here it will take the value of this I beam. Its width is, you have to supposed to take 160 millimeter, not the height, but height is taken as 400 millimeter, 430 from this end to this end, as and the 400 is the length, distance from these two bends, and 15 plus 15 is the difference between these flanges, is the length of these flanges. Now, it is to be used as a simply supported beam or equipment. The web thickness is given as 20 millimeter, and the flange thickness is given as 15 millimeter, 50 thickness. The beam carries a uniformly distributed load of 60 kilonewton over the entire, over the whole beam, whole span. The beam carries a uniformly distributed load of 60 kilonewton over the whole span. Okay, here what is seen here from this span here and from this span here, that is 60 kilonewton. Find whether the maximum bending stress is within the permissible limit of 100 MPa. If not, find the width of 12 millimeter thick cover plates to be welded on each side of the section to be safe. Also, find the length over which the plate is to be extended. So here, after the plate is welded, it is supported at this end and this is supported at this end. So initially, this beam height of length 9.6992 millimeter, and my question is whether we can have this value of the bending moment is possible here or not. Now, first you have to find out the permissible bending is within this limit or more than that, and we have to, if not, we have to do the next step. We have to do the cover plate to be welded. Now, our I beam is strengthened by thick plates is here. The permissible stress is given as 100 MPa. That is, sigma can be as most at most as 180 MPa. So we are supposed to calculate the bending stresses, whether first it is less than 100 MPa or not. If not, what is the maximum, and width and length of the cover plates for self stresses. Now, the limiting stress for I beam 160 the width multiplied by 430 is the height divided by 12 minus 150 to 400 means if we remove the value of this flanges as well as the width constant, then 150 will be the reduced to the breadth will be reduced to 150 multiplied by 20 multiplied by 400 to the power 4 divided by 12. So 260.1 into 10 to the power 6 cubic meter. That is the limiting stress for IB. The maximum bending moment will be, we know here in cases where simple supported being uniformly load, distributed loaded W will be W L square divided by 8. That is equal to 60 into 8 squares. And L is given as 8 and W is given as at 60. Means rotor intensity is given as 60. The supported span is given as 8 meter and the beam condition uniform distributed, so 60 kilonewton per meter. So if you put the value of W and L is here, so 60 into 8 to the power 8 square divided by 8 is equal to 480 kilometer per meter. So 480 into 10 to the power 6 Newton per millimeter. So sigma by Y is equal to M by I. Thus, from the bending equation, sigma divided by Y is equal to M divided by I. So sigma is up to the moment unload to S, we have to calculate. Divided by I is the distance for the extreme height, which is equal to